We will now be having a look at equilibrium constant. We know that equilibrium reactions are reversible, whereby reactants will form products, and once the products are formed, they will form reactants. Over time, an equilibrium is established where the concentration of the reactants and the concentration of the products no longer change over time. So the equilibrium constant shows the relationship between the concentration of the reactants and the concentration of the products. It is denoted by the coefficient capital K, where K is equal to the concentration of the products divided by the concentration of the reactants. So you can see it's a ratio or a relative amount. If we applied this to a particular reaction between four substances, A, B, C, and D, where A moles of A plus B moles of B is in equilibrium with C moles of C and D moles of D, K would be equal to C to the power of C, which in this particular instance denotes its moles in the molar ratio, multiplied by D to the power of D moles, and that would be divided by A to the power of A moles multiplied by B to the power of B moles. From this we can see some of the following characteristics of equilibrium constants. That it is a mathematical relationship between concentrations of reactants and products in a reaction that is at equilibrium. Every reaction has its own equilibrium constant, and this is a constant at a particular temperature. Only temperature is able to change equilibrium constant values. Where a reaction involves solid or liquids, these terms are not included in the equilibrium expression as their concentrations cannot vary. Other characteristics include that the size of the equilibrium constant gives an indication of the relative proportions of reactants and products at equilibrium, whereby a small value of K indicates that at equilibrium only small concentrations of products are present, and therefore reactants are favoured, or there would be a greater proportion of reactants. A large value of K, or greater than 1, indicates that at equilibrium the concentrations of the products will be considerably greater than those of the reactants. If we have a look at some examples of writing equilibrium constant expressions, we can see here that we have a reaction between nitrogen monoxide and hydrogen gas, where 2 moles and 2 moles are reacting to form 1 mole of nitrogen and 2 moles of water. Our K in this instance would be the concentration of nitrogen multiplied by the concentration of water to the power of 2, and that would be divided by the concentration of nitrogen monoxide to the power of 2 multiplied by the concentration of hydrogen to the power of 2. Another example shown here, you can see that the substances are all gaseous once again, so that's important to take note, and that we have carbon dioxide and hydrogen reacting to form, or in equilibrium with, carbon monoxide and water. So the K for this reaction would be carbon monoxide's concentration multiplied by water's concentration, and we would divide that by carbon dioxide's concentration multiplied that by hydrogen's concentration. A reaction quotient is actually the same ratio constant at any point in the reaction. However, it is a time when the reaction is not at equilibrium. It's calculated in exactly the same way as the equilibrium constant, but it is not necessarily equal to the K value. It is used to determine which way the reaction will proceed at any given point in time if we know the value of K. So instead of using the K as the coefficient, we would use Q. And in this particular instance, A and B would be our products and C and D would be our reactants. Let's have a look at a few calculations involving the equilibrium constant. Consider the following reaction at 425 degrees Celsius. Hydrogen is reacting with iodine gas to form hydrogen iodide gas. At equilibrium, we're given the concentrations of the different species. The first step is to write the equilibrium expression. So K would be equal to hydrogen iodide to the power of 2 divided by hydrogen times the concentration of iodine gas. Once we've done that, we can substitute the equilibrium concentrations into the equation, where K would be equal to 0.192 to the power of 2 divided by 0.0228 times 0.0284, and that would give us a K equivalent of 297. That would be if we rounded it to the nearest significant figures of 3, based on the values given in the question. You can see that this is a very high equilibrium constant, and so there is a large proportion of hydrogen iodide when compared to the proportions of hydrogen and iodine gas. Here's another example. So we're given some information here about the steps of the production of sulfuric acid, and we know that it involves the oxidation of sulfur dioxide, or SO2. The sulfur dioxide and oxygen form an equilibrium with the product, sulfur trioxide. The information given here is that 2 moles of sulfur dioxide and 2 moles of oxygen are placed into a 10-litre flask and allowed to react at a specific temperature. And that would be a constant temperature. The temperature would remain unchanged during that reaction. When equilibrium was established, 0.150 moles of sulfur dioxide remained. Calculate the equilibrium constant for this reaction. Well, in this particular instance, we're not given the equation or the molar ratio, nor are we given the concentrations of each particular substance. So we need to do all of that first before we try and input that information into the equilibrium constant equation. So here is our reaction, or our balanced chemical equation. We've got 2 moles of sulfur dioxide reacting with 1 mole of oxygen to form 2 moles of sulfur trioxide, and then the reverse reaction. In order to work out the concentration at equilibrium, we need to use what is called an ice table. So an ice table, or the I in ice, represents the initial concentration of each particular reactant and product, where the products should generally be 0 unless otherwise stated. The C in ice represents the change in the concentration based on the molar ratio, so we can use our molar calculations to work through that. And finally, our E in ice represents our final concentration at equilibrium. So first of all, we need to place the known values into the table from the information given. So we were given information that 2 moles of sulfur dioxide was placed into a 10-litre flask. So we're given moles and volume. Therefore, we're able to calculate concentration as 0.200 moles per litre. Likewise with oxygen. Our sulfur trioxide value, or concentration, would be 0. We're also given the information that at equilibrium sulfur dioxide there remains 0.150 moles. In 10 litres, that would then provide us a concentration of 0.015 moles per litre. So this is the information that we thus far know. Step 4 then is to calculate the other values and place them into the table. So here is the information that we already know. We know initially we had 0.2 mole per litre of sulfur dioxide. We know what is remaining is 0.015 mole per litre. The concentration that reacted with the oxygen to form sulfur trioxide is then 0.185. We can then use the molar ratio to substitute those values in. So since the molar ratio of sulfur dioxide to oxygen is a 2-to-1 ratio, we would divide the concentration of sulfur dioxide by 2, and that would give us the concentration of oxygen that changed or that reacted initially. Okay, so that would be 0.0925. We know that at the beginning of the reaction in the vessel there was 0.200 mole per litre of oxygen. So we know that 0.0925 mole per litre of oxygen reacted with the sulfur dioxide to form sulfur trioxide. So if we look at the difference, the equilibrium concentration should therefore be the difference between the initial and the change, which is 0.1075. Based on the molar ratio then that sulfur dioxide and sulfur trioxide have, which is a 2-to-2 or a 2-to-1 ratio, the concentration of sulfur trioxide is also 0.185. which means if we have a look at the change and the initial value of the concentration of sulfur trioxide, the difference between the two is an addition of 0.185 mole per litre to the vessel. Finally, we use the equilibrium concentration values to input those into our equilibrium constant expression. So of course we write the expression, so sulfur trioxide to the power of 2 divided by sulfur dioxide to the power of 2 multiplied by oxygen. Of course we're talking concentrations there. Step 6 would be to substitute the equilibrium concentrations from the table into the equilibrium expression. So here they are here. Finally, we come up with a K value of 1414.98. That is a very, very large equilibrium constant expression, so that would largely be favouring the sulfur trioxide production, where there would be a large proportion of sulfur trioxide comparative to the sulfur dioxide and the oxygen gas. Another example of a calculation involving equilibrium constant is given below. We're given the information that 2 moles of hydrogen iodide is placed into a 1 litre container at 25 degrees, and it is found that at equilibrium 22% of the hydrogen iodide is decomposed into hydrogen and iodide. Calculate the equilibrium constant for this reaction. So first of all, again, we need to write the equation and the molar ratio. In this particular instance, the hydrogen iodide is reacting to form hydrogen and iodine gas. It's a 2 to 1 to 1 mole ratio. Then we need to construct another ice table, and we need to input the values. Okay, so initially we have a concentration of 2 mole per litre of hydrogen iodine, where 2 moles was reacted in a 1 litre vessel. So 2 divided by 1 gives us 2 moles per litre. We know that we had no products to start, so hydrogen and iodine should be 0 mole per litre initially. If we have a look at the change in the concentration, we know that 22% decomposed. So that is actually equivalent to the change, where it's 2 times 0.22, or if we times it by the 22%, which gives us 0.44 mole per litre that reacted with or to decompose to form hydrogen and iodine gas. So at equilibrium, what's remaining of the hydrogen iodide then is 1.56, which is the difference between the initial and the change. Using the molar ratio, where it's a 2 to 1 to 1 ratio, we would then divide that change in hydrogen iodide 0.44 by 2, giving us 0.22 mole per litre change for hydrogen. The difference between that and the initial value of 0 is 0.22. So we know at equilibrium there's also 0.22 moles of hydrogen gas. Likewise for iodine gas. We use those final values in the equilibrium last row of the table in order to input that into our equilibrium constant. So we need to write the expression, of course, which is hydrogen iodide's concentration to the power of 2 divided by the concentrations of hydrogen and iodine multiplied. We then substitute our equilibrium concentrations from the table into the equilibrium expression, which is shown below. In this instance, the K is equal to 50.28. This value has not necessarily been rounded. However, we can once again see that this is a large K value, and that the equilibrium would be certainly favouring the production of the products hydrogen and iodine in this particular instance. Now you won't get all calculations showing such high K values, so you just need to make sure that you're completing this working out sufficiently that you're confident with your worked responses. Lastly, you can be given information and need to extract data from a table in order to input information into an equilibrium constant. So from the graph, we can see the nitrogen dioxide is reacting with dinitrogen tetroxide, and that it's a 2 to 1 mole ratio. We then need to gather information from the graph, of course, where we can see approximately that dinitrogen tetroxide has a concentration of 0.240 moles per litre, and the nitrogen dioxide has a concentration of 0.180 moles per litre. So I'm gathering that from the section in the graph that is constant, where the concentrations no longer change. And that demonstrates to me that there is an equilibrium there. Once I've done that, I can then write the equilibrium expression, which is of course K is equal to nitrogen dioxide to the power of 2 divided by dinitrogen tetroxide. Once again, I substitute the equilibrium concentrations from the table into the equilibrium expression. I come up with a value of K is equal to 0.98. So in this particular instance, it is slightly below the value of 1, which would show there's a slightly higher proportion of reactant versus product. And that brings us to the end of our equilibrium constant and those calculations involving the equilibrium constant. I hope that you can apply these concepts and these calculations to some other examples.